Hello and welcome to the U.S. Center. Very excited to introduce Dr. Kate Calvin, the Chief Scientist for NASA.
Thank you. Thank you, Tom. And thank you all for coming to the U.S. Center today. I'm going to talk to you a little bit about how humans are changing the Earth using space-based observations. But I want to start with this photograph. How many people here have seen this before? Excellent. This is a photo called Earthrise. It was taken 55 years ago this month from the Apollo 8 spacecraft by an astronaut named Bill Anders. And this is the first color image of Earth from space. This picture was taken as they were orbiting around the backside of the moon, and they came around, and this is what they saw. And I had the opportunity earlier this year to interview the astronaut that took this photo and hear about his experience both in taking this photo and what it's meant since then, because people around the world have seen this photo and they use it and think about it. And what he talks about is how beautiful our planet is, this blue marble that we can see from far away. And at NASA, we have been looking back at Earth ever since. So people think about us as a space exploration agency, but one of our most important missions is our home planet. And we have a number of spacecraft that are looking at Earth continuously. So this is an animation of our current Earth observing fleet. We have more than 24 satellites and instruments in orbit that are continually monitoring our planet. They can see things like vegetation, carbon dioxide, clouds and precipitation, changes in the mass of ice sheets, and much more. And we've been observing the Earth for decades, so we can see not just what it looks like today, but also how it's changed over time. And I want to show just one example of that, focusing on urbanization, since that's one of the themes of today. So this is from a series of satellites called Landsat. The first Landsat images are from 1972, and we just launched Landsat 9 recently, so we have 50 years of images. And what this satellite shows us is land use and land cover. So we can see where there are trees, where there's snow, where there are crops, where there are urban areas. And since we have 50 years of it, we can see how that's changed over time. So this particular animation is of Las Vegas in the western United States, and we're working our way up. We're now in 2017. What you see when you watch this whole animation is the city is getting bigger. So we are urbanizing. And you can see this when you look throughout the world. There's a lot of cities that are expanding. When we look at other parts of the world, not in cities, you'll also see things like changes in forests. Some parts of the world we've seen declines in forest cover. Some parts of the world we're actually seeing forest cover start to increase again. And we can see all of this because we have this 50 years of observations. One of the other things you'll just notice technically on this is the images get better as you go, because we got new satellites, new technology, and so we're able to better image and understand and measure what's happening on Earth. Urbanization isn't the only thing that's changing on Earth. So this is using both NOAA's in situ observations as well as a satellite from NASA called OCO2 to measure CO2 concentrations globally. And what you're going to see here is that CO2 concentrations are rising. So as we've been emitting carbon dioxide since the late the second half of the 1900s, we are also seeing those concentrations rise. And you're seeing this here both with satellite data and other measurements. So we can take our satellites, we can compare them to other ways of getting observations, and we're seeing the same trend. Carbon dioxide concentrations are rising. We can also look at what's driving those changes. So one of the things we do is we take our satellite observations, we combine them with other types of measurements using models, and we can understand the sources of the emissions that are driving those increases in concentration. So these are animations of carbon dioxide emissions, both sources and sinks. So what you're seeing here, there's 3 different views of the Earth, and this is just 1 year in the life of Earth. It's 2021. And what the brown is, those are fossil fuel carbon dioxide emissions, so emissions from the combustion of fossil fuels. But you see some of green, that'll be land use and land cover change. Some of the flashing you're seeing, particularly in the southern hemisphere, is carbon being absorbed. So the oceans take up a lot of carbon, as do some types of land cover, so forests and other things. And we can see that there, and we can measure those changes over time. And what you see, the previous animation I showed you was a long-term trend over years where we're seeing carbon dioxide concentrations rise due to increasing emissions. When you look within a year, you'll see some changes there, largely due to northern hemisphere summer. So in the northern hemisphere, in the summer, there's a lot of vegetation, and so you actually have slightly lower carbon dioxide concentrations. Again, the overall annual trend is a rise. Within a year, you'll see some changes within that. Carbon dioxide is not the only greenhouse gas. So we can also look at methane. And here what you've got is the same sort of information on the left that you saw before, just with a slightly different format. So that's carbon dioxide. On the right is methane. So after carbon dioxide, methane is the largest contributor to warming. It's about responsible for about 0.5 degree Celsius. Total warming is about 1.1 or 1.2 degrees Celsius. So it's a large contributor to that. It has different sources than carbon dioxide. So what you saw before is a lot of the carbon dioxide is coming from fossil fuel combustion. Methane comes from things like wetlands, agriculture, oil and gas leaks. And this is using a model to show us the total methane concentrations within a year, but we also have new satellite instruments that can help us understand where those emissions are coming from and identify super emitters. So we put about 1.5 years ago an instrument on the International Space Station called EMIT. EMIT was actually designed to look at mineral dust. So mineral dust are these fine particles that can reflect sunlight or absorb it depending on the color. And so they have an effect on local temperature and air quality. But the science team realized they could use that exact same instrument and measure methane. And since then, it's been identifying hundreds of methane super emitter sites, so places where you have large plumes of methane, and we're making that information publicly available so that people can see what's happening on our planet. So, but because greenhouse gas emissions and concentrations have been rising, we are seeing increasing temperatures. This animation is showing you monthly temperatures across there. So you're seeing, warmer temperatures in the summer, and it's going to work its way through the year. So we started in, around 1900, and it's going to work through till today. And I'm going to let it play through till today because 2023 was the hottest summer on record in North America, and you will be able to see it here. But we are seeing these increasing trends in temperature because of rising greenhouse gas emissions and concentrations. So we're still in the 60s, so it's, have some years to go. And this is where it starts to get very warm. There. And we can now see 2023. One of the things we know from science is that how much warmer it gets depends on how much more we emit. So future warming depends on future emissions. So as we're monitoring this and watching this, we can see track those changes in concentrations of greenhouse gases, as well as these changes in temperature, and help us understand where we might go in the future. So one of the other things, so I mentioned that 2023 was the hottest summer on record in the Northern Hemisphere. Part of what happens with climate change, it's not just temperatures. We're also seeing changes in extreme events and other parts of the Earth system that go along with these rises in temperature. This is from this summer. This is a heat wave in Houston. And this is just an image from an instrument on the International Space Station called EcoStress, which can measure temperature at a very, very fine or precise scale. And so we can see here the redder is the hotter. And parts of Houston on this particular day this summer got up to 47 degrees Celsius. So it's very hot. And what you see when you look at this, so you can kind of see the highways. So dark colored streets tend to be warmer. You get this urban heat island effect. You get a pavement effect. And we're seeing these very extreme heat events. And this is just one example from Houston. But we saw a lot of these very extreme heat events around the world this summer. And those extreme heat events are rising with warming. It's not just, one of the other things that happens as we have increases in warming is we're seeing declines in the mass of ice sheets. So this is an animation from a set of satellites called GRACE and GRACE Follow-On. So we have about a little over 20 years of information from this set of satellites. It's in partnership with Germany. And what these satellites do is they actually use gravity and the speed of orbits to understand mass underneath of them. And so as a result, they can track when there's a change of mass. So when you put them over an ice sheet, they can look at where there's a change in the mass of the ice sheet. And so you're seeing this with Greenland and Antarctica spatially, as well as the trend lines here. And what we're seeing is that we're having declines in these ice sheets. So as it gets warmer, the air temperature, we're melting from above. We also had a field campaign called OME, OMG, or Oceans Melting Greenland, that helped us better understand processes that happen from below. So the edges of ice sheets hang out over the ocean, and as the ocean temperatures rise, you start to melt those ice sheets from below. And so we can use these field campaigns to better understand the processes that are driving this. And what you see here, the red is where we're losing ice, the blue is where we're gaining. So you do have some gains inland in Antarctica, but along the edges, particularly here, you're seeing losses of mass. When those ice sheets melt, so right now the ice sheets are over land. When the ice sheets melt, the water runs off into the ocean, and now you have more water in the ocean. So one of the other things we see is increases in sea level. And here on the upper left, I'll start with that. That is satellite-based observations of total sea surface height. And so you can look at global sea level and see global sea level rise. The figures start in 1993 because that's when we start making those satellite observations. But we can see those trends over time. Also, with sea level rise, it has big effects on coastal infrastructure and coastal communities. And that's what you're seeing with these other visualizations. So we're seeing storm surge, coastal erosion, and flooding events associated with that. So moving on, I also want to talk about the water cycle. So as the planet heats, we're also seeing changes in the water cycle. And what we really see are more extreme wet events and more extreme dry events. So we're more droughts and more floods. And where those happen depend on where you are. So this animation started in 2002, and it's going to work its way up to 2022, and it's showing you these water cycle extremes. The red are these extreme droughts. The blue are these extreme wet events. And interestingly, this is using the exact same satellite we use to look at changes in the massive ice sheet, because it can actually show you changes in terrestrial water storage as well. But what you see as you watch this over time is that these events are increasing. And on the bottom, we've got global temperature. And on the other side, we have an indicator of intensity that's capturing extent, duration, and severity. And what you see is as the temperatures rise, that intensity rises. So we're seeing more of these events, more extreme wet in some parts of the world, more extreme dry in some parts of the world. And these different types of events present different challenges. So droughts have big impacts on agriculture communities. They can make areas more susceptible to wildfire, where floods have implications for infrastructure, for people, for moving around. And we're seeing increases in both. The next thing I want to talk about is hurricanes. So this is from Hurricane Otis in October of 2023. It was a Category 5 hurricane that made landfall in Mexico. And what we're looking here at is precipitation. So the red colors are more precipitation. This is from a satellite called GPM, which is in partnership with Japan, and it's measuring this rainfall. And one of the things we know from some people that studied climate change in hurricanes is that as temperatures rise, we're seeing a higher proportion of strong storms. So of the hurricanes that form, more of them are Category 3 through 5. We're also seeing more intense rainfall events in these storms. And that's one of the things that GPM is measuring here. So GPM can show us what's happening in Hurricane Otis, or any of these sorts of storms. But we also want to understand better what actually happens in the hurricane and what's causing those storms, and so that we can better predict them. And so one of the things that we launched earlier this year in the spring was a set of satellites called Tropics. And it's a constellation, so there's more than one of them. And what they do is they take these high frequency measurements of hurricanes. So looking at temperature, at humidity, and different aspects of the hurricane, but very frequently, so that we can watch how that storm evolves. And we use that and we provide that to our friends at NOAA and the National Hurricane Center so they can help improve their hurricane forecast, so that we're better prepared for those hurricanes that come in the future. So that was a lot on climate impacts, and a lot of those impacts we know are going to increase in the future. I want to show something different here. This is air pollution. So this is actually NOx emissions over the United States, and it starts in 2005 and it goes through till present day. But you're going to see a different trend here than we did before. So when I showed you carbon dioxide concentrations, those were rising. When you look at air pollution in the U.S., it's falling. So these red areas of air pollution, we're seeing less and less of them. And we're seeing improvements in air quality throughout the United States over the last 20 years. And this has to do with improvements in technology. So as we're more energy efficient technologies, it also has to do with changes in regulation. But we can actually see, this is from an instrument called OMI on the AURA satellite, we can see from space that we are improving air quality across the United States. So we can also see those trends, not just increases in greenhouse gases. And earlier this year, we launched a new satellite called Tempo that's also measuring air quality. So this is showing you the exact same pollutant that I showed you before, only it's a much higher resolution picture, both in terms of spatial resolution, we can now see at the neighborhood scale, but also in temporal frequency, because this is what's called a geostationary satellite. So it is just over North America, and it can give us hourly observations. And what that means is that we can, first of all, we can give better air quality alerts. We can let people that have asthma or other health conditions know when air quality is bad and better prepare for it. But we also have neighborhood-level information that we can give to people that make planning decisions, so they understand where are those air pollution hotspots, and they can take steps that they think will help address them. And a lot of what you'll see when this comes back again it's over cities and over highways. So when you zoom in, you can really see highways, and if you look during rush hour versus not, you can see the road versus the city move. And so you can see all of that. Just an interesting tangent, what you're seeing out here, when there's weather we can't observe, so there's a hurricane there. But otherwise we can see this and we can see that, the changes in air pollution. The last example I'm going to give before I open it up for questions is a cool neighborhoods project. So one of the other things we can do is look at when people make changes to the Earth's surface, how that impacts temperature or other factors. And so this is from the same instrument that I showed with the Houston heat wave, but this is looking in LA. And here in LA, they had a cool neighborhoods project where they painted the street to be more reflective. And so when you zoom in here, you can see that. So that street, it's cooler over that street than the surrounding neighborhood. And that's one of those things that we can see when people take these steps to cool their neighborhood, we can actually help identify the impacts that it has. So I'm just going to close out by an image that was taken about a year ago. It's a comparable image to the one I showed at the beginning, but this one's more recent. This is from the Orion spacecraft. And one of the things that we're doing at NASA, as we explore, we're looking back at Earth. We're trying to understand what's happening to our planet and share that with all of you and make that data and information publicly available so people can understand what's happening where they live and take the steps that they need to respond. And with that, I will open it up for questions.
Thank you. My question is, to what extent do you include machine learning in the algorithms that you use for your hurricane forecasting?
So we're increasingly using, the question if people couldn't hear, it was about machine learning. So we're increasingly using more, and so we do on some, and there's different applications of it. Some of what you can use machine learning for is anomaly detection, so you can look through satellite archives and see where things look different. We also use it some in our climate modeling, so we can use it, one of the climate modeling teams uses it to better parameterize their model because they can create these equivalents of it and better understand it. We are also using it to decide when to take satellite observations. So they use it for scheduling of when you're doing those sweeps. But we're seeing more and more of those examples over time. And as more people use it, we're getting more and more partnerships and more that we can do. And that's really important because as we're putting up these new satellites, we're getting more and more data. And so we need, help from machines to help us interpret it and understand it.
Yeah, thank you. A wonderful presentation. What type of data is needed at the household level to keep the focus on people? And at least in the U.S., since we are looking forward to having the 2030 census, what type of data do you think that could be instrumental to take this type of research to the next level? My name is Julio Witty. Thank you.
Nice to meet you, and thank you for the question. So we have a bunch of different information that can help people in households. So I showed you in the U.S. Some air pollution data that's at the neighborhood scale so that you can understand what's happening in those neighborhoods. What I didn't mention was Tempo, so it's only looking at North America, but it's a part of a set of 3 satellites, one over Asia and one that will be launching over Europe, so that you can also see that outside of the U.S. and make those same measurements for air quality. We also have information that can help understand energy access and power outages. So if you've ever seen something called the Nightlight satellite, it looks at the Earth at night. But you can use that to actually understand where people have electricity and where people don't. And so there's some researchers around the world that have used it to better understand energy access. We also have a team that's been working on energy potential, so looking at renewable energy potential using both satellite observations and models to understand where you might be able to install different types of renewables and what the potential is of those. And so we have a bunch of different things that we can look at there to provide that information.
Thank you for the fascinating talk. My name is Hiba Baroud. I'm from Vanderbilt University. And my question is, what is missing from satellite images? It seems like you've covered everything up to the neighborhood scale. The question used to be before that the issue is the resolution with satellite images going down to the household level. So what is next in satellite images?
Great question. So a couple of things. One thing is that when we launch a satellite, we have to make choices between whether we get frequent observations or global observations, as well as how precise they are. So some of these things, like when I showed you Tempo, that's just over North America, and we do have other satellites, partners that are putting up satellites over Europe and Asia, but there's parts of the world we won't be able to see with that network. And so sometimes you have that. Sometimes there's differences in frequency. So for our global orbiting satellites, they might only measure once every few days rather than once every hour. And so we don't always have frequent observations. Some of what we do is work with our partners at NOAA who can take those and make those operational. We are also continuing to add new measurements there as the new science questions emerge. So we have a couple of satellites coming up in 2024. One is called PACE, which is going to be able to look at ocean biology. So it's going to look at ocean color and help us better understand the biology of the ocean. It's also going to be able to look at aerosols and aerosol clouds over the ocean. So we're going to learn more about that. And when we look further into the future, some of the big questions around future warming are about aerosol cloud interaction. So exactly how much will it warm for an amount of emissions? We need to better understand aerosols and clouds. And we have missions planned later this decade that will help address that. So what we do is we think about what are the science questions that we have that space-based observations can help answer. And there's an entire process run in the U.S. to get those questions. And then we build satellites to help fill in those gaps.
Thank you very much. That was a very insightful presentation. I wanted to find out, generally speaking, looking at the image data that you have, what is the correlation between what the green zones actually absorb from the carbon emissions perspective? How do those green zones, like with Southern Africa or Sub-Saharan Africa and a lot of the global south as well as South America, relate to ocean capture and relate to the capture that's in the north? Thank you. My name is Mutanga Mukombe from Zambia, Rio. Thank you.
Sure. So when we emit carbon dioxide, some portion of that is absorbed by the oceans. The oceans actually absorb quite a bit of carbon. They absorb it on the surface, and then the oceans mix to get it in to move it throughout. We also absorb it over land, and how much we absorb over land depends on the vegetation. So trees absorb more carbon than barren land, and so it does vary there. But it's usually the statistic I see is about half of the carbon stays in the atmosphere, and the rest is absorbed by land and ocean. But what we do can change that. So I mentioned that trees absorb more than barren land, and so reforestation, afforestation will change the amount of carbon that stays on land and is not in the atmosphere.
Thank you. Thank you very much for this very interesting presentation. My name is Soraya Saada from Egypt, Heliopolis University. Actually, I wonder about, is there availability data about how many tons of carbon we sequester, how many saving? We always interested about what emitted. Egypt is one of countries didn't have a great contribution to climate change, but it's have a great impact, effect from climate change. So we have a lot of initiative to doing something for climate change, like regenerative agriculture for smallholder farmer in Egypt. But I wonder if there was a measurement, or you put it in your program, something to having always data about how many carbon it's sequestered or saving. If there was requested data or tools that you are interested in, because I think it's very important also to promote the initiatives that have such like sequestration of carbon or others.
Yeah. Yeah, thank you. So what satellites observe is concentration, and they're looking at the total column concentration. So they can see changes in CO2 in total. But then we can combine that with other information like activity-based data. So in the U.S., we can combine it with information from the U.S. Environmental Protection Agency, which has information about emissions from particular activities. And we can combine that using models and understand the different sources and how those change over time to get at your question. And we just launched this week a U.S. greenhouse gas center. I know I'm focusing on the U.S. I'm going to get to the rest of the world in a second. We just launched this, and part of it is bringing together some of those data sets. But one of the big principles we have, so while we're focused on our own and understanding our own emissions, is making everything we do publicly available. So you can have, you can use it in other parts of the world. And our satellite observations are global, and a lot of the models that are developed are also global, so that this can be done.
Hi, I'm Sancha. I'm a student from Boston College. Thank you for the presentation. I think it was great. I thought it was very interesting when you showed the map of the U.S. and how you had seen a decline in emissions. And I was kind of just wondering if there were any databases or tools that NASA had available to use, say, data from different time points in different states, if somebody wanted to study the effectiveness of a certain policy and its implementation in different states using data from the different time points.
Yeah, so first of all, the animation I showed of the U.S. was a different pollutant than what I was showing earlier. So just want to be clear about that. It was a different, we do actually see declines in emissions, but just want to make sure you're clear on that. We have a lot of different information throughout the U.S. government. So NASA can give us some spatial information from above, but we have partners at EPA and DOE that have other information on that. And I think maybe we can follow up about exactly what you need. Yeah. And unfortunately, we are now out of time, so I'm going to turn it back to Tom, who will let you know about the next event.
Thank you. Another round of applause for Dr. Kate Calvin. That concludes this NASA Hyperwall talk.